All right, folks. So thank you so much for sending in your questions. I'm going to go through these. I'm also going to attach my honors level video on IMF so that you can, if you want to watch for just a quick overview before we actually get to it. A lot of these questions do have to do with that. I am going to go through it with these questions, but if you want like just a quick overview that's just a little bit easier to follow rather than doing it with exact questions, take a look at that video first before you come here. And I think a lot of these questions will make a lot of sense with that. So I'm going to start with question number 17. Question number 17 asks, based on the structural formulas, which you have above, of these two things, which one is going to be more soluble in water and best helps to explain why? First thing I want to talk about is a concept that you might remember from first year, which is like dissolves like. Like dissolves like means that polar substances will dissolve other polar substances and non-polar substances will dissolve other non-polar substances. Water is a polar substance. So let's take a second to talk about why it's polar. The easiest way to think about polarity is if the molecule is symmetrical, meaning it's the same on all sides, it is non-polar. If it is not symmetrical, it is polar. Water is an easy one. We know that water's shape is bent. So if we take a look, what I usually tell my honors students to do is you make an imaginary line down the middle like this. You can see both sides are the same. But if you make an imaginary line here, the top and bottom are not the same. Okay? If you want it to be non-polar, top, bottom, left, right all need to be the same. Well, top needs to be the same as bottom, left needs to be the same as right. So that means that water is polar, and if you look at these two, propanol is also polar because the left and right are not the same. Top and bottom are great, left and right are not the same. Ethane, though, top and bottom are the same, left and right are the same. If you draw a line down the middle or across like this is non-polar. So based on our like dissolves like concepts, we can get rid of A and B, the two choices for ethane, because water is going to be more soluble with propanol, or is going to dissolve more propanol. Okay, the second part of this question gets into LDF. We're going to talk about, gets into IPF or IMF. IPF just means interparticle force, IMF means intermolecular force. They're the same thing, they're interchangeable. So there are going to be three main types of IPF that we would talk about with covalent compounds, which propanol and ethanol are. Ethane, excuse me. There are LDF, dipole-dipole, and hydrogen bonds. LDF happens in all molecules because it has to do with just movement of electrons. I'm going to get more into that a little bit later. And it also is directly related to mass. So that's what C is getting at. Dipole-dipole isn't in C or D, but I will tell you it's basically any polar molecule will have dipole-dipole interaction. Hydrogen bonding is, first of all, it's not a bond. It's an attraction. It's an IMF or an IPF. Hydrogen bonding is essentially all it is a very strong dipole-dipole. It happens between hydrogen of one molecule and an oxygen, nitrogen, or fluorine of another molecule. it's those three, nitrogen, oxygen, or fluorine, because they are very electronegative. Usually, when we're talking about IPF, we're talking about just a sample of one thing, meaning it would be just a sample of propanol, or a sample of ethane, or a sample of ammonia. And we're looking to see what IMF attracts each other to them, attracts those molecules to each other. That's usually what we would see for an IPF question, and we will see some of those in this practice. This time, we are talking about dissolving. So what does water do when it dissolves something? It breaks apart the individual molecules. Now, these are covalent compounds, so they're not going to dissociate like an ionic would, okay? It's going to stay propanol. I'm not going to draw all the extra H's because we just don't care about them very much. But you think of a sample of propanol, you have a whole bunch of propanols everywhere, right? What water is going to do, so these are all attracted to each other, and what water is going to try to do is break that up. Okay, that's dissolving, right? It breaks up the individual molecules. So here we are saying, is it because of the mass, which again I told you that is indicating LDF, or is it because of hydrogen bonding? Now we said everything has LDF. Great, okay? Maybe the answer is C. But the other trick to IPF questions is the stronger IPF you have is the one that you actually care about. So we need to see, okay, do we have dipole-dipole or do we have hydrogen bonds? And if we do, then LDF doesn't really matter. The only time you're really going to talk about LDF is when that's the deciding factor, because it's very, very weak. Okay? But here, we know we have LDF. We also know you have dipole-dipole because we just said it all happens between polar molecules, and we already said propanol is polar. Okay, so right away I'm thinking LDF's probably not the answer. It's obviously not dipole-dipole, so it's not one of the choices. So let's take a look and see if we would have hydrogen bonding. So can propanol form hydrogen bonds with water molecules? Let's draw another propanol again. I'm not going to do all the H's here again. I said that a hydrogen bond is between a hydrogen of one molecule and an oxygen, nitrogen, or fluorine of another. That oxygen, nitrogen, or fluorine also needs to be attached to a hydrogen. Is it here? Yep, it's actually attached to two of them. So this would be a hydrogen bond, which again is an attraction. We're not making new molecules here, we're just dissolving. So propanol can in fact form hydrogen bonds with water. Okay, so it's looking like D might be the answer here. But let's go to the last part here. Is it true that ethane cannot? Ethane has a bunch of hydrogens. So why can't it form a hydrogen bond? Because those hydrogens are not attached to an oxygen, nitrogen, or fluorine. They are attached to a carbon. Okay, in order for a hydrogen bond to happen, hydrogen must be attached to nitrogen, oxygen, or fluorine. And the reason is because these three elements are very electronegative. Okay? Let's go back to our propanol, excuse me. Okay, that was fun. So here, if you're taking a look at this interaction, oxygen is extremely electronegative, hydrogen is not. So what happens is you form a partial charge, and that's what dipole-dipole is as well. This is extra strong dipole-dipole because oxygen is so electronegative that we will still measure it with partial negative and partial positive because it's not ionic. It's not full negative and full positive. So we use these weird symbols for partial. But you have to know in your head, since oxygen is super electronegative, that's pretty strong slight positive. And then the same thing down here. Slight negative, slight positive. Okay, so you need to have hydrogen connected to nitrogen, oxygen, or fluorine in both molecules, because then there is a very strong slight positive and slight negative in both molecules. That's what's missing with the ethane. We have hydrogen bonding for water, but it can't hydrogen bond, which is subtraction again, with ethane because there's not a hydrogen bonding situation in ethane. In order for hydrogen bonding to work, there needs to be a hydrogen connected to nitrogen, oxygen, or fluorine in both of the molecules. Now again, remember what I said at the beginning here. Usually, you're just talking about a sample of one thing, like propanol. And you would say propanol has hydrogen bonding, great. But here they're taking it one step further and they're saying, okay, what about if we try to dissolve it? Can there be hydrogen bonding between the molecules of water? So ethane, no. Propanol, yes. All right, so now we go back to the question. I know this is a long time on one question because we wanted to review some of the IPF concepts as well. We go back to the question, and C is true. It has a greater mass than ethane, but again, that's pointing towards LDF, and I'll explain more why later. Once we have a stronger one, which we now know we have hydrogen bonding, we don't pick that. That is not the answer that best helps to explain why. It's true, but it's not the best explanation. So the answer is going to be D. So the question that was posed on your document was how do hydrogen bonds interact with ethane and propanol? I think I explained that because water has hydrogen bonding between itself, but it's not going to interact with ethane because ethane does not have hydrogen bonding. So hopefully that takes care of that one. All right, next question is 19, which is right on over here. This one is going to be particularly tricky for people who may not have done physics yet. We talked very quickly and briefly about this at one point this year, so I'm really glad someone asked about it so that we can go over it again. Okay. Temperature is the average kinetic energy. That's what temperature measures, KE. We did talk about that in first year when we did the heating curves. KE is equal to 1/2 mv squared, where m is mass and v is velocity. Velocity is the same as speed. Okay, once you know that, I think this question is pretty straightforward. This is something that if you've taken physics or you are taking physics, that's something you probably know right away. If not, we went over it very quickly once at some point this year, and now we're going to do it again. So here, what the question is saying is, for both ethane and propanol, it's at 400. So for this, it's going to be 400 no matter what for both ethane and propanol. But the difference is ethane has a 30 grams per mole mass. Propanol has 60. We don't know how many moles we have, but we do know it is the same. It's equimolar, okay? So let's just say 1, because that makes it a little easy on us, all right? So if it is 1 mole, then ethane, M will be 30. For propanol, M will be 60. So which one has to be faster? It obviously has to be ethane, because if this is 30, this needs to be a higher number to get to 400, because they're both at 400. If this is 60, then this can be a lower number to still get to 400, right? So once you know that Ke 1/2 mv squared is equal to the temp, then it's pretty easy to figure out if this number is lower, this one has to be higher. So I think the missing piece here is that we really haven't spent much time on the Ke formula. So there were probably people that just didn't know that. All right, next question, 20. Okay, 20 is a good question, a thermo question. So this tells us that the compound is endothermic, which means we know delta H is positive, which is actually unfavorable, right? So if we're looking for delta G to be negative, because it tells us why is it thermodynamically favorable, and we know this is positive, then we know this is negative, we know that delta S has got to be pretty high, right? It's got to be high enough to make delta G negative. So you can think about this question a bunch of different ways. Honestly, there are a million different ways to go through these options. But I'm going to look for the one that makes sense to make delta H go higher. Delta S go higher. So the first thing we should talk about is, what is delta S? Delta S is entropy. Entropy is a measure of how spread out the energy is in a system. Now that's kind of hard to visualize, so you can think of it as how spread out particles are in a system, because that's where the energy is. So if the particles are more spread out, the entropy is higher. Okay, and we talk about that too. We talked about how when you go from solid to liquid or liquid to gas, the entropy increases because everything is more spread out, right? So that makes sense. So what I would probably do for this question is go through the choices and say, do any of them increase the entropy? If so, I'm going to pick that one. So if you look here, starting with A, first of all, it doesn't increase the entropy. Second of all, it's just a lie. That's not true. All endothermic processes are not favorable. Okay, first of all, endothermic just relates to delta H, and that doesn't tell the whole story. We also need to look at T delta S. Second, a positive delta H, endothermic, is often unfavorable. B, stirring the solution during dissolution adds energy. Stirring doesn't add energy. To add energy, you need to heat something up. Stirring does increase reaction rate. Okay, so that could be a red herring there, meaning it's kind of throwing you off the trail a little bit. You're saying, okay, well, it does increase reaction rate. Maybe it does that by increasing the energy. That's not how stirring increases the reaction rate, though. Remember, in order for something to react, we need to have collisions in the correct orientation with the correct energy. Stirring relates to the amount of collisions. Stirring increases reaction rate because it increases the amount of collisions. So therefore, the chances that they are with the correct energy and the correct orientation are higher, right? Because we just have more of them. So stirring does increase reaction rate, and I think that's what they're trying to throw you off here. But it doesn't add energy, and it doesn't change delta S, which is kind of what we want to happen here. So I'm going to get rid of that one. Dissolving the salt decreases the enthalpy of the system. Quite frankly, I've never heard of that being a thing, that dissolving would increase enthalpy. Also, that's not what we're looking for here, right? We're looking for something with delta S. I guess if it did decrease the enthalpy and made the enthalpy negative, that would make sense, but it says it's an endothermic process. It's not going to change that by dissolving it. I just don't think C makes any sense, to be quite honest. So the answer must be D. And let's think about that. Dissolving the salt increases the entropy of the system. What's dissolving? Dissolving is spreading out the K from the NO3. We're just taking those two pieces and breaking them apart. That's spreading out the particles more. Spreading out the particles more is spreading out the entropy. So D does make perfect sense. Okay, let's go to 26. All right, 26 is an IPF question. It's interesting. Because we have this is an organic compound, and it's an acid. It's an organic acid. It's not something that we really spend a lot of time on in this type of class. They're never going to expect you to know how to do this. That's an advanced course that's after this course. But what you can see here, based on our kind of introduction of IPF, is that there is going to be dipole-dipole, and there is going to be hydrogen bonding. Because we have a hydrogen connected to an oxygen, and then presumably you would have another molecule where there's hydrogen-oxygen connected, and they'll have hydrogen bonding. Okay, this is different from the other one I did earlier in the video because it does not have to do with dissolving. It has to do with just a sample of these acids. Fluoroacetic, chloroacetic, bromoacetic, iodoacetic. Okay, it's just a sample of those. There's nothing else in there. There's no water. So we're just taking a look at this. Okay. The trick here is that all of them have hydrogen bonding, and all of them have dipole-dipole because they all have this. The only difference here is that for fluoro, this X is an F. For chloro, this X is a Cl. For bromo, it's a Br. And for iodo, it's an I. Okay, so we don't need to, this is a rare instance where we don't need to talk about those stronger ones because they're all going to be the same. They're happening over here, right? That's where the hydrogen bonding and dipole-dipole stuff is happening. That side, which is the same for all four of them. So it doesn't matter as much here. Okay, so I would get rid of anything that talks about dipole-dipole or hydrogen bonding. So that takes B and D. Again, the reason I would do that is because it's the same for all of them. The dipole-dipole forces are not going to be stronger or weaker because it's the same. That's where the dipole-dipole forces are going to be. However, the LDF will be different. So let's delve into LDF a little bit more with this question. LDF is a temporary dipole, okay? The reason it happens, let's take a break from this question and just talk about LDF. The reason LDF happens is because electrons are constantly moving. They never stay in one place, okay? So for example, say you have chlorine, and I'm just going to draw a chlorine atom like this. Great, okay? That's what the chlorine atom looks like, everything's spread out. But those electrons that make that little ball that we think of as an atom are constantly moving around. So at one point, we could have tons of electrons on one side and not on the other. So if we were here, we would say this side is slightly negative and this side is slightly positive just because those electrons are over there. I really wish there was a different way to show slight positive and slight negative that shows like sometimes it's really strong slight positive and sometimes it's really weak. But there isn't, so we still use the same symbols. You just have to know that right now it is super weak. This lasts for a very small fraction of a second. And then the electrons move again. And let's say now the electrons are up here. Right? So we have a slight positive here where there are less electrons and slight negative here. And then what if we at Cl, I'm just using Cl, by the way, to show the nucleus. I'm not drawing all that stuff. And then we have this at one point. So this is going to be the positive end, and this is going to be the negative end. All right, now again, this lasts for like a fraction of a second. It is a temporary dipole. A dipole, for those of you who might not remember from first year, is when you have a slight positive and a slight negative. That's a dipole. This is very temporary, very quick. So it's a very weak attraction, but it is actually very important because it happens all the time in every molecule. The other thing to know about LDF is that the more electrons there are, the stronger the LDF will be. And that makes sense, right? Because you're going to have more electrons moving around. So if there's more electrons that go here, it's going to be more negative and then more positive here. You know, so like the more electrons there are, the stronger the LDF will be. It's always going to be pretty weak, but the stronger it will be. And so the way you'll usually hear that communicated is the higher the mass or the molar mass, the stronger the LDF will be. Kind of misleading because like mass isn't really electrons, but that's usually how it's communicated. Because you know mass comes from protons and neutrons, so if you have more protons, you also have more electrons. So that's usually how you'll hear it. The higher the mass or molar mass, the stronger the LDF is going to be. Okay, so that's just a quick overview of LDF. For this question, you also have to know about the relative strengths of our IPF. So remember, we said LDF is the weakest, then dipole-dipole, then hydrogen bonding. Here, we're just going to be looking at LDF, but the same principle applies. The stronger the attraction is, the harder it is going to be to break up those molecules. So stronger attraction means higher boiling point. Stronger attraction, higher boiling point. Because you're going to have to put in more energy to spread those molecules out. So if we're going from liquid to gas, that's exactly what we're doing. We're adding enough energy to spread the molecules apart. The stronger attraction, the more energy you need. So here we're looking for the lower boiling point. So we want the weaker LDF. Which one has the weaker LDF? The one with the smaller mass, which you know is, what are we looking at? Chlorine and iodine, which we know is chloro. Okay, so the answer must be A. Even if I didn't know the thing about the mass, we're never going to pick the one that's a stronger force to be a lower boiling point. That's just not a thing. Stronger force, higher boiling point. Okay, so there were 2 questions on this on your document. How does LDF affect the boiling point? We talked about the stronger the attraction, the higher the boiling point. What is LDF? We also talked about that. Very weak attraction that has to do with movement of electrons. Temporary dipole. All right, I'm going to take a little break, and I will come back and continue on with the practice test. And I'll try to put these videos all together so that it's just one long video for you, but if not, I'll make a bunch of them.